This is the lesson video for the second example in 8.3 Day 2 where you're doing volumes of solids of revolution. So it looks like the exact same graph for this one, and it is. It's the exact same functions, it's the exact same graph. But this time you're going to take the curves and generate a region, or generate a solid, by rotating the region bounded by the curves and the line y equals, around the line y equals 2. So what I'm going to ask you to do first is pause the video and on yours, sketch the region, shade it in, add the labels for the equations of the boundary lines and the line that it's being revolved around, but all of them, they're actual equations right near the curve. And then come back and see how you did. Okay, so you should have then, you should have something like this. And take a second, pause the video, sketch the solid. It's going to look a little bit like the one we had before, that kind of funny funnel, except this time that it's going to be opening to the left and meeting and those endpoints to the right. So as you think about this solid, what we want to consider is this made from full-size circles being stacked together left to right? You can see the circle here on the end. Or is it being made from washers? Something has a hole in the middle of it so that there's an opening in the middle of the solid. And what we can see here is that there's every single one of these places would be a filled-in circle when it rotates around that line y equals 2. So this should be a solid disk. You want to sketch that disk then and see if we can add in some labels that indicate the measurements about that disk. So as you start to sketch the disk, you want to draw that kind of top to bottom circle. And as we sketch the disk, we want to think about where those things came from. So this is our rotation line y equals 2. And the curve had been beneath it originally, so at every location, the radius of that circle up here is really the difference between the curve y equals 2 and that curve. If they're not expressed in the same terms, meaning if one's in x and one's in y equals, you may need to rewrite functions. We're in good shape here. So our radius comes from the value 2, subtracting the value that comes from that square root of x function that the radius comes down to. So high curve minus low curve in the sense to get that length. So the area for the disk then is area of a circle, pi times our radius, quantity squared. Almost all the hard work is done now. I've got my boundaries marked on here. So the last thing I want to do is figure out how to get the volume for this. Now that I've got radius, I want to figure out the volume, and the volume is where your calculus finally comes in. It says, well, you want to add up the volume of each of those individual disks. And those individual disks, their volume will be their area multiplied by the generic thickness, delta x in this case. Our variable of integration should match the variable that all our expressions are in the terms of. That should also match our bounds. So we need x bounds for this integration. And the first places this has is an x of 0, and the last place that this has is an x of 4. So we're integrating 0 to 4, and again, either by hand or by other means, and we're looking at a volume of about 8.378 cubic units.